All right, so on page 34, we once again have a free fall example with two objects. We're still going to have two objects in free fall, except this time it's two rocks, and this time they're going to give us no numbers, just variables, okay? So it says an object A is thrown down from the top of a building of height h. At the same time, object B is tossed straight up from the ground. The objects collide halfway. So remember last time with Superman and Lois Lane, I said, don't assume halfway unless told otherwise. Well, here they're telling us halfway, okay? Number 1 says, what can you conclude about their average speeds? So don't forget our defining equations. What is average speed?
Distance over time.
Right. So distance divided by time. It doesn't matter who's going up or down. And if they collide halfway, don't they both have like height divided by 2 as their distance? And then the time from release to the time that they hit is going to be the same. So I don't know that time, but I know that the distance and time are going to be the same, even though one's speeding up and slowing down. Because of the same, they're going to have the same average speed. Good deal? Number 2 says, what can we conclude about the final speed of the objects just before they collide? Now this one actually has an edit. And so if you're reading the answer choices, final, there's an average in there. Let's change that to final. Okay. We're comparing the final speeds of A and B. And so, you know, we just found average speed. And so average speed is also equal to, and I know SV, I'm sorry, speed velocity, I know, but that initial plus final divided by 2. Now here we're throwing both of them, right? And so to solve this final velocity, multiply both sides by 2. And then I have to subtract the initial velocity. Okay. One speeding up, one slowing down, right? And so who's going to have the greater final speed? Or you can think.
The one that starts from the ground.
Right. No, it's not dropped. It says it's thrown. Oh, thrown. Yeah, so we're throwing one down, we're throwing one up. One is speeding up, one is slowing down, right? And so here, and you got to think of direction if you want, you know, you got a negative here. The one thrown down is going to be negative, so it turns positive, right? And so, and this is assuming that they're relatively the same initial throws, magnitude-wise. And so B is probably a good estimate here. Now we're given a little more guidance on number 3. It says you're now told that the initial speed of A is V, and object B has twice that, so 2V. Which graph is going to accurately reflect the position time graphs? So when I first look at these 4 graphs, they all kind of feel the same, but to me, D stands out. D has a diagonal. Now that doesn't mean, oh, it's different, so it's wrong. But should these objects in free fall have diagonals? No. And so a diagonal would mean constant velocity, which is wrong. Free fall is constant acceleration. So D is wrong. And the others, gosh, they all feel kind of the same. How about y'all look at A, B, C? Which one can I get rid of? But most importantly, why? Why can I get rid of C? Okay, so we've got one increasing in slope in the positive, right? What is this one doing? Increasing in slope too in the negative. Do both of these objects increase slope, increase velocity? No. So C should not be, because both increase velocity. And so that leaves A and B. And if you look at their shapes, they actually have about the same shapes, okay? There's a couple differences here. Can you find one difference that makes one more correct than the other?
On A, they intersect about halfway.
Okay, so A shows an intersection. And by the way, these are not ghost balls. They don't pass through one another. So we're just really looking at time equals 0 to the collision. That's really what we're looking at. And so they told us up above that they hit midway. So right there, we can say, you know, B is not midway. There's another indication of why A is more correct than B. Look at the beginning of that top B. It starts with no slope. This would be an initial velocity of 0. That would be what it is if we had dropped the top marble, okay? So final answer, A is the most correct. Good deal? All right, everybody take a deep breath. We're about to do some variable solving. So this always freaks people out, especially here in the beginning. And no, it's not all this challenging, okay? This one, you've got two objects moving, and so that's a little bit of a challenge. We've got opposing directions, but I'm going to make a simplification and help simplify that. And we're solving for three different things, okay? On the AP exam, maybe there's 1 or 2, 3, maybe multiple choice that are variable solved. And maybe there's one part of one free response that you have to variable solve. So we do it to practice for the big day, right? And so, assuming the two objects have not yet collided, so we're going to pause midair. How far apart are the objects sometime after being thrown? Now watch this. State your answer in terms of T, V, H, and a fundamental constant. Fundamental constant, what kind of constant are we dealing with in free fall? Gravity. So they're saying you can have G. So that last sentence is basically saying when you solve for how far apart, when you say, you know, delta H or delta Y equals, those are the only letters that can appear in your answer. If you want to think of those as legal variables, I can't have anything else. I can't have a generic A. I can't have, you know, D. I need to put everything in those terms. Does that make sense? Okay, so not yet collided. I don't think I've drawn a picture yet. So let me draw a picture. So top of a building, ground, ball A, we're throwing it down, right? Ball B is getting thrown up with 2V now, they tell us. And thankfully, they said we are colliding midway, but just not yet. I'm not going to draw that yet. Because this one is saying, well, freeze, what distance separates them at any time? And so I'm going to show, you know, what if ball B and A are frozen right there? Can we solve for this delta y separation distance? Okay. Well, they told us the height of the building is h, and I know that a travels a certain distance or displacement down, right? So I'm going to say delta ya, and b travels a certain distance or a certain displacement up. And so I'm about to change our direction on us, because when I look at all these distances, even though I don't have a d, but if I look at all these as distances, I can do a summative statement, a scalar adding statement. I can say that h, the height of the building, is equal to that distance that a travels plus the distance that b travels. But if they haven't quite collided, there's a separation distance. And that's what we're trying to solve for. So this is a scalar summative statement. Just remember that. All right, h is allowed, but delta y is not. So I need to get some kind of equation, expression to plug in there that does have the allowed variables. So I'm going to start with a. And so if you recognize, hey, I know the initial velocity, I don't know the final velocity, I'm probably going to be using that first equation. I'm sorry, second equation. Now I wrote it in terms of displacement because here's the change. Since I really only care about the distance that they're going, what if I say, well, A is going forward. What if I make its forward direction positive? And B is going its own forward. So what if I make it positive? Because really we just are adding distances here. And so with that, I know that delta YA, it started at a velocity down. So I'm going to say a positive V. T is okay. They said I can have T in the answer. Plus 1/2. A is the acceleration due to gravity. It pulls down our positive direction. So I'm going to just sub in a G. And then T is okay, but I got to keep the square. And in a minute, that's what I'll plug in right there. Well, pause. Let's do the same for B. So B is going to get thrown up. We're saying up is positive, forward direction for B. And same equation, because I don't know the final velocity of B. And so its initial velocity is 2v. Time is okay to keep. Plus 1/2. Now watch out here. Gravity is acting downward on ball B, right? There is a direction change. And so I'm going to say a negative G and then T squared. Everyone okay? So since adding distances to equal a total height, so I'm really just looking at these as distances. I don't care that one falls and one goes up. I'm just adding the individual distances. So it's a scalar summative. Okay, so I just said forward is positive for each. So good question. I don't think AP would count it wrong if you said -10 for gravity, but usually with variables, you keep the variable. And the others we don't know, so you can't plug anything in there. And this is the equation we're going to plug in there. All right, so now let's plug them in and see what happens. I get H, that's allowed, equals VT plus 1/2 GT squared. That's the distance of A, plus the distance of B, We got 2vt. Now, 1/2 times a negative g, doesn't that basically same thing as negative 1/2 minus 1/2 gt squared? And then plus that separation distance that we're looking for. And so now what do we notice? I got a lot of variables. Can I combine like terms? Vt and 2vt, 3vt, and then I've got positive 1/2 gt squared, negative 1/2 gt squared. So gravity doesn't care if you're rising or falling, right? And so that just goes away. It's 1 minus 1 type. And then plus that separation. And so all that chaos, for a simplified answer, we'll just subtract 3vt from both sides, and there's our separation distance. So for distance, direction doesn't matter. So we're just saying forward. So on the one that's thrown down, A, gravity is the same direction that its forward direction is. But in B, gravity is downward, opposing the ball's forward direction. So the way I define positive, since in the end, this was just scalar, I was really just looking at distances. And so those three distances that add up, the one thrown up isn't going to go as far because gravity's resisting that forward motion. So it's got to be the opposite direction there. All right. Number 5 is going to go quicker. The hard part-ish is done. Okay. So that's our answer to number 4. And then number 5 says, how much time passes from when they were thrown? Now we're going to collide. And it says, give your answers in terms of VH. Oh, we can't use T. Hey, we're solving for T. And a fundamental constant, gravity. And so now we're looking for time. So this is number 5. We're looking for time. Well, I saw time in the previous equation, right? Maybe we start there. And so H minus 3VT equals the separation distance. If you collide, what's the separation distance between the two balls? 0. So if you collide now, which we are in number 5 and number 6, this zeroes out. And so I'm going to add 3VT to the other side. H will equal 3VT. To solve for time, you divide both sides by 3V. Notice this answer is all I need. They said you can have H and V and G, not that you have to use every single one, but notice I don't have any other letters. Now the 3 is a factor, that's not a variable, it's okay. So there's my answer to number 5. Zoomers, y'all okay? Let me know if you have a question. And then number 6, now the physics isn't too bad in number 6, okay? The math, we're going to be doing a little bit more with the math, just FYI, okay? It says, what must the object A's initial speed be in terms of just H and G? So those are the only letters that can appear in my final answer, okay? And so that initial speed, we'll notice that we have an equation that has speed in it, right? So they're still colliding, so we still assume the collide, okay? And we're just looking at A. And so we know it was thrown down at V. It's accelerating at G. Remember, we said down was positive. And we just found the time to the collision. So notice I'm using my answer from before. And then what else? Oh, if it goes halfway, midway for the collision, then its height change is going to be half the height of the building. We don't know final velocity. That's okay. We're going to use the equation that doesn't need the final velocity. So it's going to be that delta y, and again, this is all of a, VOT plus 1/2. I'm going to say a for right now. We'll plug in a g here in a second. And so we start plugging in. We know h over 2. We're looking for that initial velocity. The time we had was h over 3v, and it's okay. If you're already seeing v is going to cancel out there, it's okay. Plus 1/2 g, and then I need that t again, and don't forget to square it. So I'm going to go in and square everything individually. So it looks yucky, it'll simplify. Now it's really just math, okay? So you'll notice that in the second term, v times h divided by 3v, that v goes away. But it's okay, I got another. And so let's spend some time with that last term. I've got basically when you add when you put the numerators together, we get gh squared over, let's see, a 2 in the denominator, a 9 in the denominator. 2 times 9 is 18, and then I've got the v squared. So I end up, so far, with this. And we're trying to solve for v. Now notice I have h in every term. What can I do to simplify the h's? Say again? Divide the whole thing by h, right? And so we'll end up with 1 over 2 equals 1 over 3 plus gh not squared, right, over the 18v squared. Now, kind of combining like terms, I guess. Let's put those two little fractions together. And so I'm going to subtract 1/3 from both sides. And so I get 1/2 minus 1/3. What do we do whenever you subtract or add fractions? Common denominator. So common denominator. And so that would be 6. So I get 3/6 minus 2/6 equals 1/6, but don't forget to bring your other part down. It equals gh over 18v squared. Almost done. Mathematically, what's our next step? Multiply both sides by 18v squared. We basically cross multiply, right? And so we would get, so cross multiply, it's a proportion format. So we'd get 6gh equals 18v squared. Next step. Divide both sides by 18. And 6 and 18 reduce to 1 and 3, right? Final step is to do our square root of that business. Final answer, v equals square root of gh over 3. And I think that's what they wanted, right? Let's see. And we have g and h. Yes, initial speed is what we solve for, and g and h are the allowed variables. So that's our answer to number 6. Good deal? Okay, so let me